Not gonna show up today. We're gonna skip class. Yeah, can't do that, but almost anything else.
Oh, you can.
Well, I could, yeah, but. Okay, but first, so questions on the homework. So 10.3 is due today, I think. Questions on 10.3? Yeah.
Well, I was lost on 23 trying to do it. So.
Okay, so 23.
Oh, no.
Okay, who has that? Do you have the printout? Find a unit vector that is orthogonal to both I plus j and I plus k. So with 10.4, that's actually pretty easy, but with 10.3, we don't know about cross products yet, so. I plus j and I plus k. So with 10.4, this is not a problem. All you just do is take the cross products, right? So you know this guy is 1, 1, 0. This guy is 1, 0, 1. And you simply just take the cross product of both of those. You'll get a vector orthogonal to both. But let's say we didn't know that. How would we go about it? How do we know it has to be orthogonal to both? Huh? Dot product is 0. So let the vector be x, y, z. Let's figure out what that is. So I need that 1, 1, 0 dot x, y, z must be 0. And I want 1, 0, 1 dot x, y, z to be 0. Okay. So what's this?
X, Y, 0.
What?
X, Y, 0 equals 0. You mean like the dot product?
X plus y
Oh, okay.
equals 0. Remember how the dot product works?
yeah.
We did that yesterday. Multiply corresponding components, add them together. This one says x plus z equals 0. Right? So pretty much choosing any three numbers, there are an infinite number of answers to this problem. Choosing any three numbers x, y, z such that x plus y equals 0 and x plus z equals 0 will work here. So you can literally just make some up. Right? So let's say I let x be 1, y is minus 1. So if I force x to be 1, it has to be here, 1 here. So my z would also have to be minus 1. Right? So a possible answer is 1, minus 1, minus 1. Right? Or I could have let x be pi, so y would be minus pi. Right? Or I could let x be 7, and this would be minus 7. Or let x be 0, this would be 0. They'd all be 0, the 0 vector. I assume they want non-zero vectors. But yeah, you can just... Oh, well, with this guy, just divide by 1 plus 1 plus 1. So I would get 1 over radical 3, comma, minus 1 over radical 3, comma, minus 1 over radical 3. Right? Once you have a vector, finding the unit vector is not difficult. You just divide by the magnitude. So you do whatever you want and then divide by its magnitude, and that's it. Just make sure whatever numbers you pick, these two equations satisfy, and that's it. But yeah, in 10.4, just taking the cross product would have worked. You don't really have to think too much. Okay. Other questions?
33.
33. Okay, I need the other. Okay, so it says show that they define a new kind of vector called the orthogonal projection of B onto A and they define it to be b minus the projection.
Wait, so they just made that up and that's
Yeah, they're defining this to be
Alright.
that expression. They're saying this is a new kind of projection we're going to talk about. This is its definition, and show that that is orthogonal to the vector A. Okay, so I believe John, is it? Yeah, you saw me in the Turing Center and I gave you the hint to this. Did you actually figure out the full solution? Like, what did you do here?
I took the right side and dot product at the vector A.
And what should the result be?
The result is 0.
Right, so you know, again, if you're looking for something orthogonal, you check that the dot product is 0. So it means that we need to check that b minus the projection of b onto A. If I take that guy, dot product it with A, the result should be 0. Right? This is what we're not sure about, right? So we're going to check this. Right? What is this guy actually equal to? If I take b minus the projection of b onto A, dot product A equals, what did you get here?
After expanding the projection b onto A, then distributed the dot A to both the A dot B minus A dot projection.
Right, so there were a list of properties I gave you, and those list of properties says that dot products distribute across sums, right? So there's a property that has that. And it's also commutative, so b dot A is the same as a dot B. I just write it like this because I felt like it. And, okay, what did we go do from there? This is a dot B minus,
You expand the projection as the formula says. It's the A dot B over the magnitude of A squared times the dot product of A, the vector A squared.
it was what?
Sorry. It's another dot A.
There's a dot A?
No.
There's not a dot A.
I thought it was the A.
It's just a regular multiplication, right? Be careful how you use the dots, they mean things. Right? So this is, if this were a dot product, this guy would be a scalar and this wouldn't make any sense. Okay, so now what?
A.
There's another rule that says this guy is a scalar, so there's a rule that says we can actually factor scalars out. Remember that? So there was a rule that says we could actually put this guy in front, a dot b, over this guy squared, and this is just a dot a.
Which is equal to A squared.
Right, which is, this is actually equal to the magnitude of a squared, that's by another property, so this will actually cancel that, and then you'd end up with a dot b minus a dot b. Gives you 0, right? And a dot b is a scalar, which is why you get the scalar 0, right? It's not two vectors. If you're subtracting two vectors, you get a vector 0. But these are scalars here. Yeah, but that's it. So we've shown that if you dot product this with that, the result is 0. It means they're orthogonal. Other questions? Yeah. 41. Let's move over to the other board. Okay, so we want to show that the distance from a point to the line, so one thing I want to emphasize here is we're in 2D, right? Because ax plus by plus c equals 0 in 3D is actually what?
Plane.
it's actually a plane. We didn't get there yet, but I just want to throw that out there. If you have this expression and you're thinking in 3 dimensions, it's a plane, not a line. So just notice we're in 2 dimensions here. So we have to show distance from a random point, which they call P1, which is x1, y1. Notice that they only gave you 2 coordinates, which further shows you that we're only working in 2 dimensions here, to the line ax plus by plus is, so we're given a distance formula here, ax1 plus by1 plus c over a squared plus b squared. So basically the idea is we have some line here, which is ax plus by plus c equals 0. There's a random point somewhere else, and by distance we always mean the perpendicular distance, right? So if you map this down perpendicular to that, I want to know what is that distance. Call this d. What is that? So that's the idea. Any ideas on how we can do that? Anyone? Plug in what coordinates to the point?
The problem gives an equation of a line and a point, but then it says like show that this formula works.
Yeah. You have to prove that this is actually the formula.
Yeah.
Right? You have to prove that d will actually be equal to that expression. That's the first step.
It kind of looks like a projection of a line of vectors.
Right, you can sort of look at it as a projection. What projection would you want to do?
That's the
Would we need a vector projection or a scalar projection? Scalar projection, because we want a distance, we want a magnitude, okay? Scalar projection onto what?
the vector onto the line.
You want a scalar projection on this line? Yeah, if I can get a scalar projection onto this guy, I can find its magnitude. Okay, so how do I get a scalar projection on that guy? Right, so if I pretend that I could have made a vector going here and get a scalar onto that vector, how would I do that? Yeah. Pretty much again, pick a point here. Call it x2, y2, right? And you create a vector here. And what we can do is project this vector onto this one with a scalar projection. Right? So if I call this, so this is my vector d, and I want the magnitude of d is what I'm after. And I call this vector, I don't know what we want to call it, e. Then what I can say is the size of d is actually equal to the scalar projection of p onto d. Right? And I take absolute values to make sure it's a positive distance. So that's going to be that. So how do we figure out what that is? Okay, so let's actually look at what these vectors are. So it's x1 minus x2, comma, y1 minus y2. Okay. How do we figure out what the components of d looks like? I'll give you a hint.
P
Start
cosine.
with what the vector on this line looks like.
Never mind.
What would the vector of this line, the equation of this line look like?
The 0.
You don't need another point. think in 2D, right? The equation of a line. How do you know? What do you do with the equation of a line?
You mean as if it goes 0?
What?
Never mind.
No. Obtain the slope, right? The slope, our way of direction in 2D is slope. How do I figure out the slope of this line and write it as a vector?
It's the ijk thing, right?
Only I and j. We're in 2D. There's no k.
Oh.
How do I figure out the slope of this line? So you have y would be equal to what?
Negative a over b.
Negative a over b x, right? So now if that's the slope, what do you think, how would I describe that with a vector? What's the slope? Think back to algebra, right? When they tell you the slope, they give you a formula for it, a mnemonic to remember what it is.
Rise over run.
Rise over run, right? It's a vertical distance over a horizontal distance. How would I describe that as a vector? Where does the vertical distance go? Where does the horizontal distance
b negative x.
go? Right? It's rise over run. Right? So this is rise, so that's the vertical component, so that I put in the y coordinate. B is the run, so that goes in the vertical component. Now if I know that, I have a random two-dimensional vector, and I asked this question last class, if I give you a random guy and ask you, find a guy that's orthogonal to that, what would you pick?
Dot product.
So we know that the line direction is b minus a, which means d I can think of as, how do I pick numbers here to make sure the dot product there is 0? A comma b, right? You switch them and change the sign. Okay, so that's my d. This is my p. How do I find the component? Oh, there's a formula for it. Use the formula, Jhevon. That's right. Right? So what's the formula for the component? Of p, d, and let's take absolute values here. So it's absolute values of, well, what was it? P dot d
Over the absolute value of p. Right.
over the absolute value of
P.
what?
D.
Sorry, this is d over the absolute value of d. Okay, so that gives us, what does that give us? So p dot d, I just dot product this with that. So I take a times this. So this is ax1 minus ax2. B times that plus by1 minus by2 over, what's the size of d? Starting to see some light here. All right, starting to see that. Okay, this is all in absolute values. How do I simplify this? Factor what?
You know
Factor
that
A and B.
negative ax2 and negative by2 is equal to c from the line equation.
Right, so look at, this is actually ax1 plus by1 minus ax2 plus by2, right? And this I know must be equal to c,
Negative c.
negative c, because it's on the equation of the line, and that it must fit this formula, right? So this is negative c, but I take a minus of negative c, which makes it plus c, and so this would be ax1 plus by1 plus c over, absolute value of this is just itself, right? So I can just write this. And so that's the distance formula. In 2 dimensions, the distance between a point and a line, if you want to use vectors, this is how you'd actually find it. Right? This is a new distance formula, which you can it's easier to generalize this to 3 or more dimensions. So That's why they actually look at the distance from them in a different way. So that's actually the distance one. So this is the size, the distance between the point and the line is equal to this. Okay, so now that we know that, now the access to use it. Find the distance from the point -2, 3 to the line 3x minus 4y plus 5.
Wait, what do you want, sorry? What happens to, but how does the x, like, the x that, like, ax2, how does that equals, like, ax2 plus,
Because it was a point, x2, y2 was a point on the line. And the equation of the line says it's ax plus by plus c equals 0, which means that ax plus by equals minus c. So if I plug in a particular point, x2, y2, that's on the line, it must give me minus c. So I can just replace this expression with minus c, and I end up with. I could have also done that here with the x1, y1, but I didn't want to because x1, y1 would be the given point. It's the only actual information I know for sure. x2, y2 is an arbitrary point I picked. I don't even know what their values are. So if I can get rid of those, that's nice, and I can because of this formula. Yeah, so what's the distance from this point to that line?
Just plug it in.
So distance equals, you take the absolute value of, it's ax, so you take a times x1 plus by, so it's b times that, so it's a minus 4 times 3, plus the c, all over the radical of a squared plus b squared. That's of minus 6, minus 12, plus 5 in absolute values over, that's 9 plus 16, right? That's right, over 25. So that would give me minus 1, minus 13, so that's 13 over 5. We'll stop there. Pass your homeworks up to the person in front. I will. Okay, let's try to finish 10.4. Last time we looked at the dot product and the cross product. What were some important facts about the dot product? So I'll call. So how it's defined, so let's say I have A1, well, we were just doing this, so B1, B2, what's that?
A1, B1 plus A2, B2.
Right, just multiply corresponding components, add them together. There was a formula that relates the dot product to the angle between two vectors. So if I have A and B, and the angle between them is theta, then I have what formula?
The dot product is equal to magnitude of A times magnitude of B times cosine theta.
Right. From this we can say that if A dot B equals 0 means A and B are orthogonal.
And if it's 1, are they parallel? Oh, well, not that.
Nope. You can't really say what happens if they're parallel. Not from the dot product anyway. Okay. What we learn about the cross product? How was it defined? Give me the shortcut.
A times
Not the formula with the angle. How it's actually defined. What goes along the first one? I, J, K. What's the second row? You put the vector A along the second row. And this one? Right? You do that determinant thing that we learned last time, and you get this huge long formula that no one's going to remember. Okay, what's the, so if I know this is A, this is B, angle between them, what formula do I know with the cross product?
It's A2
magnitude of A times
Magnitude
magnitude of B times sine of
Magnitude of A times magnitude of B times sine of theta gives us what? No.
is the magnitude.
Magnitude of the cross product. What kind of quantity is this?
Vector.
It's a vector quantity. Right? This is a scalar quantity. It cannot be equal to a vector. What kind of quantity is this?
Scalar.
It's a scalar quantity. Right? Okay. Yeah, so far we did that. I think we actually did an example where we found a cross product. How does A cross B relate to A and B?
If it's equal to 0, they're parallel.
Sure, we know that, but that's what I was looking for. It's orthogonal to both. That's its main selling point. That's one of the reasons why it's most useful to us. A cross B is orthogonal to both. And of course, with this formula, it actually tells us that A cross B is 0 if A and B are parallel. Right? So know these guys, know their definitions, know how to think of them in terms of angles, and know what they actually mean. Right? When this guy is a 0 scalar, it means that they're orthogonal. When this guy is a 0 vector, it means they're parallel. You need to know things like that. And you need to know especially that A cross B is a vector that's orthogonal to both. So if you ever need to be perpendicular to two things at the same time, the cross product is what you're going to want to use. If you ever want to check that something is orthogonal, the dot product is what you're going to want to use. So let's move on from the cross product section. Let's talk about some other things that the cross product gives us. Here's a problem. Find a vector orthogonal to the plane containing the points 2, 0, minus 3, 3, 1, 0, 5, 2, 2. Ideas.
vectors on the plane using 2 points each, so these vectors.
Right, so we have 3 points here. Pretend they all lie in the same plane, so there's a plane that contains these points. Let's say I put P, Q, R. And yeah, you can actually create 2 vectors, as he said. Like using 2 points at a time. Doesn't matter what 2 vectors you create, they'll both be parallel to the plane. Okay, so what would this vector be? The vector PR. Right, how do we create a vector from 2 points? Final point minus initial point, right? So 5 minus 2, that gives us 3. 2 minus 0, that gives us 2. 2 minus a minus 3, gives us 5. PQ done the same way. 3 minus 2 gives us 1. 1 minus 0 gives us 1. 0 minus a minus 3 gives us 3. So we have these 2 vectors. Right? So now I want a vector that's orthogonal to the plane. How do you think I'd find that?
Cross product.
Cross product those 2 vectors. That will actually give you a vector that's perpendicular to both at the same time. Since these guys are parallel to the plane because they're in the plane, something perpendicular to them will be perpendicular to the plane. So this guy is going to be, I can do PQ cross with PR. So the vector we want can be PQ cross PR equals IJK. What goes here? 1, 1, 3. PR is 3, 2, 5. So this can give us a vector. So remember how we did that? How do we do that?
Block the column on the right.
Which column and row?
Like for example with I.
With I. Block out the I column and row. I get this guy, right? So it's 5 minus 6, comma. In the second one, what do? You have to take a negative sign, right? Remember there's a plus minus pattern that goes on here in the background. So it's a minus sign of what? Block out everything in his column and his row, and then you do that determinant again, cross multiply. This times that. So it's 5 minus 9. Then the last one is going to be what? Two minus 3. Right? So for the k component, you block out everything in his row and his column. So you have 1, 2, 3, 2. Cross product here, get 2. Cross product there, get 3. You get 2 minus 3. So the vector we want would be the vector minus 1. This would be 5 minus 9 is minus 4, but you take a negative of this, so it's plus 4, and 2 minus 1. So that is a vector that is orthogonal to the plane. I never mentioned this, but notes. Cross product follows the right-hand rule. So for direction of A cross B, take your right hand, point in the direction of B, stick up your thumb. The direction of your thumb is the direction of A cross B. So for example, if I wrote something like A is here and B is here, pretend these are 2 vectors on the blackboard. where is A cross B going? So use your right hand, point in the direction of A, curl towards B, stick your thumb up. It means A cross B is actually pointing out of the board. Right? So it's orthogonal to the blackboard, but it's pointing out of the board. So in this case, A cross B out of the board. If instead I had A like this and B like that, right? And I'm looking at A cross B. How would I figure out where it's pointing? I know it's orthogonal to the board, but it can be pointing out or it can be pointing inwards, right?
Like this? Let's go like
I have to go the other way, right? See, if I do this, I can't curl towards B because it's my right hand, right? I can't get my fingers up, right? So what I have to do is I have to turn my hand around this way, point like that, and curl towards B. Now if I stick my thumb out, it goes into the board. Right? So A cross B is going that way now, through the wall, into the board. So you can always have an intuitive sense of where your orthogonal vector is going. Remember, you can have two vectors that are orthogonal, one and it's negative. But if you want to know in particular where is A cross B, you do that right hand rule and it's telling you exactly where it's going to be pointing. So in this case, if I did, here I did PQ and PR. Is this actually the correct direction for PQ cross PR?
I think, assuming that PR is B, it would.
Well, for PQ cross PR, I have to do my right hand this way to do that and stick my thumb. Technically speaking, PQ cross PR is pointing down. Right? This would actually be PR, PQ.
Oh, because you put your hand on
Right?
A and then.
Because you have to do your right hand rule. The first guy gets here, and then you curl towards the second guy, and you stick your thumb up. It will be pointing down.
So then technically we should have originally drawn it out with the down.
Yeah. But it actually doesn't matter. They say find a vector. They never said a particular one. So either one would just find it.
So does every plane, that means every plane has two possible vectors to be orthogonal to it?
Yes.
But only two, or can it have more than two? I mean, I know
Only
you can
two.
move the
A
vector
plane
around.
would have only two.
Okay.
Something like a line would have infinitely many. And in general, other surfaces, it depends on your location. So they can have infinitely many as well. Okay, let's move on. What's the next thing I wanted to tell you? Some geometric useful properties of the cross product. Say I have a parallelogram. This side is A, this side is B. How do I find the area of this parallelogram? Area of a parallelogram.
Isn't it based on height?
Which height?
No, height, you have to draw a line.
The vertical height,
Yeah.
right? So if I draw that and call that guy H, the area would be A times H, right? It's base times perpendicular height is the area of a parallelogram. Let's say though, I actually know this angle, right? What is this guy going to be?
B sine theta.
It's going to be B sine theta. Right. So now, we're in 3 dimensions. This is a random parallelogram floating around in 3 dimensions. This, think of it as a vector. This, think of that as a vector. What is this? This would be the magnitude of the vector. So the length of this will be the magnitude of the vector A. So the area would be equal to the base times the perpendicular height. Well, what's that guy?
Cross product A and B.
No. The magnitude of the cross product. So it turns out if you have two random vectors in space and you want to figure out what's the area of the parallelogram that they create, it's the magnitude of the cross product. So this gives area of parallelogram. That's a geometric interpretation to the magnitude of the cross product. Parallelogram created by A and B. So that's one geometrically useful property. Other properties of the cross product, we have to know how to do arithmetic with them because that will be important many times. So if I say A, B, C are vectors, C is a scalar. Here's one property. Let's say I do A cross B. Is the product commutative? Can I switch B and A with no consequence? No, we just did that whole right-hand rule, right? It actually makes a difference, right? This is actually the minus of B cross A, right? So with this kind of product is not commutative. If you switch the things, you get the opposite vector. Right? So like I said, sometimes the obvious rules aren't obvious. This kind of multiplication of vectors, you can't swap the entities without something happening. But what if a scalar times this? It turns out we can still factor out scalars. That's actually not a problem. This is the same thing as this, which is actually the same thing as this. So scalars behave well with the cross product. The cross product can also be distributed. So if I have A cross product with the vectors B plus C, it is A cross B plus A cross C. Order matters here, right? So it's not okay for me to say this is B cross A and C cross A. It's not true. The order of multiplication matters with the cross product. So you have to write it just like that, or else you will mess up. Okay, what else do we have? It goes the other way as well. So if I have A plus B cross C, this is A cross C plus B cross C. 5. I can mix a dot product and a cross product. Right, so this is a dot product, this vector dot product with the cross product of two vectors. It's actually A cross B dot C. What if I combine two cross products, A cross B and B cross C? This actually gives me A dot C times B minus A dot B times C. So cross product doesn't distribute across itself, right? The formula becomes this. Right? So those are some useful facts. I'm not sure if I actually problems in the homework where you'll need this, but you typically need it somewhere. This is one that's going to show up all the time, so be careful of that. Scalars are pretty well behaved, but the distributive laws are really weird with the cross product, so that's something you should make a note of.
Wait, for number 6,
Yes.
like outside the parentheses, so you're multiplying B how? With a cross product, a dot product, or just... Oh, I see.
A dot C is a scalar. So this is just a scalar multiple of B, and this is a scalar multiple of C. Time do we have? 1 minute. Let me just tell you something about property 5, and then we'll stop. It's actually the last thing I wanted to talk about in this section anyway. We also talk about torque in this section, but I'm skipping that because it doesn't usually show up. But you can read it. That's for the physics application. So the dot product we could apply to figuring out work. The cross product you can actually apply to figuring out torque. But I'm not going to talk about that. What I want to mention here is triple products. This is the left side of property 5 is called the scalar triple product. Of A, B, C. You could actually define it in a nice way using determinants. So A dot B cross C is actually a scalar defined by A1, A2, A3, B1, B2, B3, C1, C2, C3. So if you find a determinant of that matrix, it's the same as finding that expression. What this is, A dot B cross C gives the volume of V. It's called a paralleloiped, defined by ABC. What do I mean by that? Let's say I have the vector here. This is the vector A. That's the vector B. That's the vector C. They're pointing in 3 different directions. If I start to create a parallelogram, so with side AC, I create one side of a parallelogram with AB. I create another part of a parallelogram. I reflect the other side here, and the other side reflected here. So this parallelogram, if I think of these vectors as being on the corner of a parallelogram, the volume of this parallelogram is A dot B cross C. Which means if A dot B cross C gives us 0, the scalar 0, then the vectors, it means that this volume is actually 0, which means all the vectors lie in the same plane. The ABC lie in the same plane. And in this case, they're called coplanar. So in the homework, they're going to ask you, are these vectors coplanar? This is what they mean, if they're all vectors in the same plane. And a quick way to check is to just do this. And if you get 0, they're coplanar. If you don't get 0, they're not. That actually ends 10.4. So homework for that is due on Tuesday. And we also have a quiz on Tuesday on all the Calc 3 stuff that we've done. So 10.1 through 10.4, quiz on that on Tuesday. And the homework for 10.4 due on Tuesday as well. Stop there.
You gave us a quick warning as like how to deal with the properties.